Thanks for the introduction, Katie. I'm Erika. I'm a postdoc in the Scalable Solvers group. And the title is a little bit misleading. I shortened it down to just an introduction to wavelets. And so this is going to be a little bit different from the previous talks. It's going to be a very high level overview. This is a topic that I only recently started learning about because it's something that I heard about and decided that I needed to get to learn more about it. So let's say we have some very complicated data set. So this data set could be temporal. For example, this might be a radio signal, or it can be a spatial data set. So you can imagine some fluid, there's some fluid flow or some velocity field, and we want to know what that velocity field is at some point in time. And so in the context of this talk, it doesn't really matter if it's time or space. I will probably use the words interchangeably as well. But the idea is that we want to present this data efficiently. And so as standard mathematical techniques, we represent this data using a basis expansion. And the idea is that we want to find a basis set such that the number of terms in the sum is as small as possible. And so that's what we mean by efficient. So you all are probably very familiar with the standard representations, the delta function basis, and then the Fourier basis. Just as a quick recap, the delta function basis, the basis functions are delta functions, and so they provide information about our data set at very specific points. However, they don't provide any frequency or spectral information about our data. And so at the bottom, on your left-hand side, those are the basis functions in real space and Fourier space. And then the diagram in the middle shows that even though shows the uncertainty in our basis. So we have good information about, we have good temporal information. So delta t is very small, but then delta omega, the uncertainty in our frequency domain, is quite large. On the flip side, we have the Fourier basis. So as you all know, this gives us very good information about the frequency in our data. But because these basis functions are not localized, they don't provide any spatial information. And so now we have large uncertainty in time, but good resolution in frequency space. And so this is these two ends of the spectrum sort of capture the uncertainty principle, which states that the uncertainty and frequency times the uncertainty in space, or real space, is a constant. And so we always have to be trading off that information. The idea behind wavelets is that we sort of find some middle ground. The basis functions both have spatial locality and spectral locality. As shown in the middle diagram, we have these functions can have a different, they can be more or less local in time or space, but at the cost of having more spectral uncertainty. And these basis functions, they typically look like wave packets, and these are essentially just like little oscillations that are localized at a specific point in space. So this, using wavelets has been useful in a variety of fields. The most common example is signal processing. And this is because in signal processing, we might have signals of very different frequencies, but they're also all transient. So because of this transient behavior, we can't use Fourier basis because you don't have periodicity. Additionally, it's believed that in turbulent dynamics, wavelets might be very efficient in representing these structures. And this is because in turbulence, we have very fine scale features, and these features actually get more and more fine scale over time. And they also, once they're superposed with each other, they can form large scale coherent structures like vortices. And so in both cases, we need spectral and spatial information, and that's what wavelets can provide. Okay, so let's get down to what wavelets are. So wavelets are actually, the wavelet basis is actually defined by a single function called the scaling function. And so we take this function, an example is shown down with the green line. The scaling function, we generate the wavelet basis by scaling this function. So like scaling the domain of the function, so it's making it wider and more narrow, and then also translating the function in our grid. So the figure on the grid shows different levels of resolution indexed by J, and also different positions indexed by K. And so we often group the basis set functions by resolution. So j equals 3 is going to be a subspace, and then j equals 2 is going to be a subspace. And ideally, this scaling function is going to be defined such that these spaces are going to be nested. And so that means a higher resolution basis function is going to be able to completely capture the lower resolution basis function. So here's a little bit of a simpler example. You can focus on the figure in the middle. Our scaling function is just a rectangle, and the blue are the scaling functions at resolution j equals 2. And then combining two of them together gives you the scaling function at j equals 1, which is the red dashed curve. And so you can see the same thing with the triangle basis function. So now that we have nestedness, we can also define an orthogonal space between the different resolution spaces. And so this is highlighted in the red, the shaded red area. And so again, in our simple examples with these rectangular basis functions, we have a small rectangle, the same basis functions as before, but instead of adding them together, we're subtracting them. And then that's how we get what I call psi. And psi is going to be called a wavelet function. And so this is maybe a lot of information. So here's everything put together. So this is, again, the rectangular scaling function. This is called the hard wavelet. It is the simplest example of a wavelet. And at the j equals 0 case, like the course's resolution, our basis function is just going to take up the entire grid from 0 to 1. At the next highest resolution, j equals 1, we have rectangular functions that are defined on each half of the grid. And then a wavelet function shown in red looks like that. And we see that if you add this red function to the coarse blue function, or if you subtract the two, you'll get the higher resolution basis functions. We can continue doing this to get to the next highest resolution, j equals 2. So this is what that would look like. Okay, so in terms of actually representing a function, just as standard basis representations, we sort of we project our data onto these basis functions. And note that we can sort of split it up into two categories. There's the coarse grid, we use the coarse scaling functions phi. And then after that, we use for the higher resolution information, we use the wavelet functions. And this is because all of these wavelet functions, when added together with the coarse scaling functions, will generate higher resolution scaling functions. And so there's no loss of information here. And as usual, as like a standard transformation, the coefficients of these basis functions is just given by the inner product of our data and the basis function, assuming we have orthogonality. So one thing I wanted to point out is that this choice of basis it's not set in stone, I will say. So I can choose what I'm defining the coarse grid to be. So for example, I can say that my coarse grid is the 0th coarseness level, and so it's just uniform. But I include all of the other wavelets in shaded red. Or I can say my coarse grid level is going to be instead contain 4 grid points, and then use the remaining wavelets as for the higher resolution features. Okay, so there are many different types of wavelets. I mostly did examples with the hard wavelets because it's the easiest. And then depending on what features you want, you can have different kinds of, you can formulate different wavelets. For numerical simulation, the thing that most people end up using interpolating wavelets because it has good useful properties for nonlinear PDEs, especially. Okay, And with that, I'd like to summarize. Wavelets are multi-resolution bases. The basis functions exhibit some degree of spatial and spectral localization. And there are many different types of wavelets. And so many extensions include multiple dimensions, multi-wavelet systems, and we're always looking for using them for practical applications. Thank you for your attention. Have a good day.